Welcome everyone to the Spoken Nerd. My name's Connor McDonald and man oh man, it is that webinar time of the year, isn't it? I've had Lock, Dev Live, I've got the Romanian user group, OD Tug, All India Oracle user group, Office Hours, Apex Connect. It's been a very, very busy time for me on Zoom. And that's why this episode is perhaps a little bit late. My apologies for that. Also, I got my first vaccination shot recently, and that certainly knocked me about a bit. So on that note though, please, if you're listening, do your best to stay safe and healthy. Follow your local guidelines, whatever they might be. Particularly a shout out to my friends in the Indian community. Some of the things I'm seeing on the news there are scary to say the least. So please stay healthy. I'd love to be able to meet you all again in person one day soon. Still, no excuses on my part. I need to try keep to a 3 to 4 week cadence on the podcast. In the last episode, we spoke about every index being a bug. That certainly raised a bit of controversy. A few people reached out to me on Twitter to debate that topic with me, and that was very entertaining indeed. In this one, we're going to return back to our back to basics topic, and that is, rather than talking about indexes being a bug, I just want to talk about how indexes work. How are they internally defined inside the database? What is their structure? In a very high level kind of view, just to help you keep in mind how index structures can be best utilized to make your applications successful. Just one quick commercial before we get underway. I did mention Dev Live. That's our series of events that Oracle are running. If you Google for Oracle Dev Live, you'll get to all the recordings of the completed events plus notifications of what's coming up soon. But most importantly, you'll also see a link to some of our offerings there called Oracle Live Labs. These are 100% free workshops you can do on your own database or on our cloud database, and many of them are tailored such that you can run them on the always free elements of our cloud database. There are dozens of labs already up on the site, and they're a great way of boosting your Oracle skill set. I want to stress there's no registration needed, no single sign-on, no email, no credit card, no nothing. Literally for Oracle Live Labs, it's just click and go. So hopefully you'll find that very useful. Okay, back to indexes. What is the magic power of indexes that lets you find data quickly? Firstly, I hope we understand the concept of a row ID. If not, please check one of the earlier podcast episodes on the row ID. But in brief, because the database is made up of blocks, typically 8K, to find a row, you need to know the block. To find that block, you need to know the file it sits in. You need to know what block in the file that is, effectively an offset from the start of the file. And you need to know the row in that block. Those three elements, the file, the block, and the row number inside that block, are all you need to uniquely find a row in the database. I should stress that row ID is not stored on the table, because if you can get to a block with a table scan just by scanning through a file, when you chance upon a particular block with some data of interest, you already know what file you're in because you're scanning it. You already know what block you're in because you're scanning it. And simply by scanning through that block, you'll hit the row of interest so you know what row you're on. You don't need to store the row ID on a table itself. It is implicit. Where row IDs are stored is inside an index. An index is a structure that is designed to let you quickly find a row ID for a particular value of interest. Applications rarely have a function that is, for this given row ID, go find some data. It's always, for this user-provided information, a surname, a social security number, or a mobile phone number. With that information, I need to find the rest of the associated data. An index is a structure that lets you associate those particular values, phone numbers, emails, etc., with a row ID, because when that row ID is known, you have the file, the block, and the row, so you can immediately go to the row on disk to find the rest of the associated data with a single read. The key thing there is, of course, the index structure. If it takes 10 seconds to scan a table, but it also took 10 seconds to scan an index to find the row ID you wanted, then there is no point in having an index. An index must be a structure that can be scanned quickly and efficiently for a known value. Otherwise, there is no benefit to having it. You may as well just scan the table it was based on. To understand that index structure, we're going to head into metaphor territory. I will warn you in advance, whenever I talk about metaphors, my partner Genevieve says to me, you should call them metaphors because they are so poorly contrived. But hopefully, bear with me. If you don't like my metaphors, please shout out to me on Twitter, but I'll do my best. I'm holding here in my hand an excellent technical book. It's actually my book on mastering Peel SQL. And oh my, yes, that is a shameless plug. I will be honest, my Mastering Peel SQL book is quite out of date now, so I would recommend other resources for Peel SQL. But I'm going to use this book as an example. Like most technical books, there's a fairly large index at the back of the book. That is the first useful part of the metaphor here when we talk about index structures. The index is associated with the book, but it's a separate thing. In the case of my tech book, it's typically at the back, but it's not part of the book itself. It's effectively attached as a separate structure in the final pages. The book content is our table, and the index at the back of the book is a separate structure which represents our database index. Also, it's worth noting, the tech book is larger because of the presence of this index. There are more pages in total. This book cost more to produce due to the presence of the index. It's the same with the database. Indexes consume more space. That means I need a bigger disk footprint. It means backups may take longer. If I have some errata in the book, not only do I need to change the pages in the book when those corrections come in, I need to correct any index entries as well. You can see where this metaphor is going, can't you? It's going back to my podcast episode on every index is a bug. There's a cost to having an index, and therefore you only have as many indexes as you need to have a successful application, and ideally no more. The reason we have an index at the back of a tech book, and in particular my Peel SQL book, is such that we can find topics of interest rapidly. Let's say I'm looking for anything in my Peel SQL book related to the topic of pipes. If you're not familiar with pipes, there's a concept called database pipes, referred to by the database package dbms pipe. For us, let's just focus on the word pipes. As a human being, how do we find this in the index? Normally what I'll do is grab the book, I know the index is roughly at the back somewhere, and I'll simply grab those index pages and open up somewhere in the middle of the index. The first thing I might see on the page is, say, the word jobs. So I know I've landed roughly in the index on the J section. The moment I see that, I know I'm interested in the index section of the remaining pages of the index, as in from J onwards, because pipes comes after J. I'll typically use my thumb or finger to divide the remaining part of the index at about the halfway point again and open that page. The first thing I might see on that index page is the word row type, so I know that I'm in the R section. I've overshot the section on pipes. So I'll jump back a few pages and then I hit packages. So now I'm in the P section, so I'm close to the word pipes. I probably won't do any more jumping back and forwards. I'll probably just skim forward from the word packages. I'll pass over things like parameters and parsing and pinning, and bingo, I'll hit the word pipes. That index entry will tell me that pipes are on page 112, and I can now go to the page in that book of interest. I'm done. Page 112 will tell me about database pipes. The index contents in a database are very similar to the index contents for my book. I have a value of interest, something I wish to search on, e.g. pipes, packages, parsing, etc. And I also store alongside that value a reference back to the source content in the book, page 112 in this case. In database terms, that reference will be the row ID, a reference back to the source data in the table. So just like in a book, where an index contains a list of topics plus a reference back to the source data, an index in a database contains a set of value row ID pairs for each value on the column or columns that are indexed in your table. If you'd like really nitty-gritty details on exactly how that information, those value pairs, are stored in index blocks, check out my previous episode on block internals, but this one is much more high level. The key thing to note here is that I didn't examine the entire index section of my technical book to find the topics on pipes. I used what I could probably loosely describe as a divide and conquer approach. Start about halfway through the index, see where I landed, and then decide on which section of the index to move to next. Then I divide that, see where I land, and decide where to go to from there, etc. Eventually, I got close enough to the topic of interest, namely my keyword of pipes, that I stopped chopping the index into sections and I simply scanned forward along the index entries until I hit the reference of pipes, which told me to go to page 112. And lo and behold, you'll probably be unsurprised to discover that this is almost exactly how indexes inside the Oracle database works. Let's explore that in a little more detail. I should clarify the episode title a little bit more of how an index works. Because inside the Oracle database, we have standard B-tree indexes, which is what we're going to discuss today on this episode. But we also have bitmap indexes, reverse key indexes, lob indexes, compressed indexes, virtual indexes, bitmap join indexes, and other forms of indexes throughout the technical stack. I'm going to focus on just the standard usage in the interest of brevity, and I'll keep referring back to our book metaphor along the way to help with that understanding. So it's just standard B-tree indexes we're talking about here. When I've got my tech book and I'm looking for the index section, I generally know it's going to be at the back of the book. That's the most typical place. And I also know that I'll need to typically start my index search probably halfway through that index section. In the case of a database, I need probably something better than I think my index is somewhere over here, near the back of the database. Thus, every index has an entry point, and we call this entry point the root block. Whenever you need to probe an index to find some information in the database, we start at the root block. For the more savvy tech listeners, before you leap onto Twitter to express your outrage, I'm omitting the concept of a fast full scan for now. In this case, all entries start at the root block. Whereas an index in a tech book is at the back, how do I know where that root block is? If you recall back to the episode we did on block fundamentals, I discussed a thing called the segment header block, the one block we store for each segment in the database that tells us how to find all the other blocks for that segment. For an index, immediately after the segment header block, we always store the root block. So we always know where the root block is. It's equivalent to the back of the book. We always know exactly where to start. When you first create an index on an empty or very small table, that root block might be all you need. If my PL SQL tech book was only 10 pages long, say, I might be able to fit all of the relevant index information on a single page at the back of the book. Similarly, if my table has only 10 rows, there is probably enough space in my single 8K root block to hold the index values, e.g. packages, pipes, parameters, parsing, etc., and the row IDs to point to the associated table data, i.e. the page in my tech book. Of course, if you forked out your hard-earned cash for my PL SQL book and found it was only 10 pages long, you probably long since have thrown it away, at which point you no longer have the book or the index. You could think of that as a truncate. Let's assume that my table is larger than 10 rows in size. Eventually, the number of rows in the table will mean that the index values for a particular column will no longer fit in that root block. I can equate this to my starting with the book index about halfway through it, not really with the intent of immediately finding the values of interest, i.e. database pipes, but more really to decide where to branch forward or backward in my index depending on the values I discover on the page I landed on. I initially landed on the page containing the word jobs, so I knew I had to jump forward to get to the letter P. This nomenclature also applies to a database index. The root block, when it can no longer hold all of the index entries, becomes what we call a branch block. Rather than holding the index entries and row IDs themselves, it contains just enough information to allow us to branch in the right direction to find the values you're searching for. If I return to the book metaphor, the root block, which is now a branch block, might contain representations that in sentence phrasing could be like this. If you want information from A to F, then go to page 1 of the index. If you want information from G to N, it's in page 2 of the index. And if you want information from P to Z, then it's in page 3 of the index. Thus, when I'm searching for the topic of pipes, I didn't find it in the root block, but the root block told me to go look in page 3, from P to Z, and look there. This is that divide and conquer concept I discussed earlier. From a database perspective, the pointer in the root block to index page 3 is simply a link or an address to a different block in the index. If the size of the book gets so large that the root block or first entry in the index can no longer hold enough information to point to the index entries, then the root block can be modified to point to a series of branch blocks, and each of them can now point in turn to blocks that hold the value lookup data. If the book was even larger again, well, I probably need to speak to my editor about how things got so out of control. But from a database perspective, the root block can point to branches, and those branches can then point to more branches, and so forth until the final database branches once again point to index blocks that contain our value row ID pairs. My use of terms such as root block and branch block allude to the other common metaphor we use for an index, namely that of a tree. And indeed, the structure of an Oracle index is based on the computer science data structure called a balanced tree. Extending that tree metaphor brings me to the final piece of terminology. Once I've navigated from the root through the branches, the blocks which ultimately hold those value row ID lookup pairs are, unsurprisingly, called leaf blocks. We have roots, branches, and leaves. The term balanced, when we talk about a balanced tree, also means a special property of every database index. Unlike a tree in nature, which has all sorts of patterns in terms of the way it grows, the number of branches it has, etc. With a database index, when you start from the root, no matter how many branch blocks you go down to, when you finally arrive at the leaf blocks, every single leaf is the exact same distance in terms of the number of branch blocks from the root block. Because of this, you can think of an index as having a height. No matter what leaf block you're looking at, it is the same distance from the root. For example, if I go from a root block down to a branch block, and then from that branch block down to a leaf block, the height of that index is 2, root to branch, branch to leaf. In the data dictionary, you'll also see an attribute called B-level. This is simply the number of branch levels, and therefore it's the index height minus 1. For this reason, don't be surprised to see an index with a B-level of 0 in the database. If a table is small enough such that its root block is also the leaf block, that is, it contains the index value row ID pairs right there in the root block, it has no branch blocks, and therefore its B-level is 0. The maximum B-level is 24, and you might be thinking, does this introduce a limit on how many rows that can be in an index? I would say yes and no. With a simple index key, such as an ascending sequence number, you can typically get about 1,000 rows in an index with a B-level of 0. That is, just the root block can hold about 1,000 value row ID pairs. Once you introduce a single level of branches, so the root becomes a branch to other leaf blocks, you can get about 300,000 rows with a B-level of 1. Once you jump to a B-level of 2, you can get about 200 million rows. So even at B-level of just 4, you would be starting to head into the trillion row mark. I don't know how many rows you can get with a B-level of 24, but let's just say there probably isn't enough disk in the world to hold it. I'll put a blog post reference in the show notes that has a demo of how many rows you can get for each B-level as it increases in size. It's just a PL SQL procedure I ran to explore how big indexes get in terms of their branch levels. Given that an index with a B-level of 2 can already hold millions of rows, it's probably useful to revisit the metaphor of tree, because often when people are drawing indexes to represent an index, it'll look like a triangle or a pyramid-shaped object with the root block at the apex of the pyramid at the top and the leaf blocks at the bottom. But in reality, a much better picture would be a very, very, very short tree that literally covers an entire paddock or perhaps an entire continent. Indexes are incredibly flat and wide because only 2 levels covers millions and millions of rows. 3 levels covers billions of rows. This is what makes them very efficient when you're scanning for values. You've probably seen those TV shows where contestants have to guess the price of, say, a car or some other valuable thing in order to win it. And as each contestant makes a guess, the TV host says something like, "No, it's higher," or "No, it's lower." And the contestants are effectively doing a binary chop to get closer and closer to the right price, at which point someone wins. We don't do that with a database index. For a 100 million row table, it's only going to have a B-level of 2, which means it's only going to be a couple of blocks I need to read and traverse to get down to the leaf block I need. This is the key element that makes indexes so incredibly efficient to search for a single key value. Even with billions of rows, it's going to be just visiting 3 small blocks to get to the exact information you need. One of the ways the database achieves this incredibly compact and flat wide structure is with a thing called branch block compression, which I stress is not related in any way to the license compression features you may have heard about the Oracle database. Branch block compression is part of every index, and let me return to my book metaphor to help explain it. I mentioned earlier when my root block became a branch block in my technical book. When I was trying to find the book topic of pipes, my root block now contained information to branch to 3 pages. If you want information from A to F, it's in page 1. Information from G to N, it's in page 2. And information from P to Z, it's in page 3. Notice in that phrasing, there's no mention of the word pipes or packages or parsing, parameters, none of the actual values that I'm storing in my index. It's just if I want from P to Z, go to page 3. I only need to reference the letter P because that's enough to tell me that pipes, packages, parsing, parameters, and in fact anything that comes after the letter P as well, is all in page 3 of the index in my book. This is an example of branch block compression. I only need to store just enough information in the branch block, P, G, A, etc., to guide me down into the leaf where the full index key information is held. We do the same thing in database branch blocks. They don't store index keys as such. They store a compressed version or just enough of an index key to decide where to navigate to next, either the next level of branches down in the index or to the leaf blocks sitting underneath them. This is one of the reasons why we can store information so incredibly densely in branch blocks, and that's why so few levels are needed to store billions and billions of rows. Don't get me wrong, there are additional compression facilities available for indexes in the Oracle database. We have a basic compression facility and some other ones which are part of the advanced compression option. These generally are all about compressing the data inside the leaf blocks because the branch block compression is already so good. So I hope this gives you a good primer into how indexes are structured and stored in the database and why they're so effective at locating rows in a table as long as you're not trying to locate too many of them in the case of a non-unique index. I haven't covered every possible nuance that comes with index usage in terms of uniqueness versus non-uniqueness or things like coalescing and rebuilding and advanced compression, etc. But the intent here wasn't to dive too deep. The intent here was to give you some simple metaphors that you can return to when you're thinking about how indexes work and where they might best be utilized when it comes to building applications. Thanks very much for listening to this episode. Hit me up on Twitter if you have any questions or requests for podcast episodes. I'll be back soon with another episode to help you be more successful with the Oracle database. Bye for now, everyone. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.